Today's lesson is on other types of regression. So not all data is linear, most are not. So we will look at various types of data that produce different type of regression equations that best fits the data set. So a regression equation is just a trend equation that shows the relationship between two sets of data. It can be used to make predictions that are shown in a scatter plot. Feel free to pause this video at any time to catch up. All right, so yesterday we did linear. In the calculator, that was number 4, and the equation is y equals ax plus b. The graph of a linear function is a straight line either going up or going down. Quadratic is number 5 in the calculator, and that formula is y equals ax squared plus bx plus c. And a quadratic graph is a U. Logarithmic is number 9 in the calculator, and that equation is y equals a plus b ln x. And the calculator gives you these equations, so you don't need to memorize them. A log graph looks like that type of curve. Exponential is number 0 in the calculator, and that is y equals a b to the x. And you have exponential growth, and you have exponential decay. A power function is actually a in the calculator, and that is y equals ax to the b power. And they look like that. Okay. All right, pause it if you need to. All right, remember that you must put data in the calculator in list 1, which is L1, which is your x values, and L2, which is your y values. They create a scatter plot. After finding the regression equation, you will also need the correlation coefficient, which is your R value. The closer R is to -1 or 1, the stronger it is. So we've talked about that. All right, example 1. Below is a scatter plot of data. Which equation best represents this set of data? So you're just looking at the picture, and remember that a quadratic makes a U, and our graph is not a U. Linear is a straight line. This graph is not straight. Exponential can either be exponential growth or exponential decay, which this looks like exponential growth. I'm going to say it's C, but let's talk about logarithmic. Logarithmic looks like this, which is not what our graph looks like. So exponential is the best one. All right, B, they haven't given you a scatter plot. They've actually given you a table of data, and they want which regression equation best represents this set of data. So we're going to have to use the calculator for this one. Before we go to the calculator, let's identify what each answer choice is. So A has x in the exponent, so that makes it exponential. B has x to the second, so that's quadratic. C is mx plus b, which is linear. And D has a number, x, and then a number, which is a power function. Okay. All right, so what we need to do is we need to go to stat in the calculator. And edit, and put in this data. So 1, 2, 3, 4, 5, to 2.3784, 2.6321, 2.8284, and 2.9907. Okay, we're going to go to each of these, the exponential, the quadratic, the linear, and the power, and write down the R value to find which one best represents the set of data. So stat over to calc, exponential is number 0, enter, 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 and the R value is 0.798, 0.798. Sorry, I think I may have done something wrong. Let me check my data. 1, 2, 3, 4, 5, 2, 2.3784, 2.6321, 2. All right, there's my mistake, sorry. 2.8284. Okay, now over to stat, over to calc, exponential. Enter, enter, enter. Okay, that's better. The R value is 0.9733. So I need to write that down. 0.9733. All right, I go back to my calculator. This time I'm going to quadratic. So stat, calc, quadratic is number 5. Enter, enter, enter. The R value is 0.9986. This one only gives R squared, so we will use that. 0.9986. C was linear. Go back to the calculator and do linear. Stat, calc, number 4. The R value is 0.985. .985. And the last one, power function, is letter A. And the R value is 0.99999. So, which equation best represents the set of data? You want the one closest to 1. So the answer is D, because it is closest to 1. Okay. All right, C, below is a regression equation. You can see they did quadratic. And the question is, if X is 24, then what is Y? So here's how I would write my equation. Y equals, the A is negative 2.786. X squared goes next to that. Plus your B value is 16.214X. And then C is negative 9.4. Well, they tell you X is 24, so you're simply just going to plug in 24 wherever you see an X. Negative 2.786, 24 squared, plus 16.214 times 24 minus 9.4. So in my calculator, you just need to type that on the main screen. Negative 2.786 parentheses 24 squared plus 16.214 parentheses 24 minus 9.4. And you get negative 1225, which is answer choice B. Remember, you can pause or rewind this video at any time. All right, example 2. A student is trying to determine the half-life of radioactive iodine-131. He measures the amount of iodine-131 in a sample solution every 8 hours. Below is his data. Write an exponential model that fits this data. So circle that, exponential model. So I need to put these in stat. I need to put this data in stat, and they want me to choose an exponential model. So let's clear out what we have in there. So 0, 8, 16, 24, 32, 40, and 48. 4.8, 4.6, 4.51, 4.39, 4.29, 4.14, and 4.04. All right, so exponential, scroll down, it is 0, enter, enter, enter. Let's go at least 3 decimal places. So that would be 4.792 parentheses 0.996 to the x power. So the way I write that, y equals 4.792. You can put a times. I prefer for you to put a parentheses 0.996 to the x power. All right, how much is left of iodine 131 after 55 hours? So hours is on the left, is your x value. So x is 55. So I'm simply going to plug that into my equation. So I do 4.792 parentheses 0.996 to the 55 to the 55th power. So you type that in the main screen of your calculator, 4.792 parentheses 0.996 to the 55th power, and you get 3.844. Okay, C, what is the half-life of the substance iodine 131? Well, this is my starting value, 4.792. You could also look up in the table and use that one, and you'll get close enough to the same answer. So that's your starting value. You want half of that. So if I do 4.8 divided by 2, I want there to be 2.4. That's the amount I want left. So by half-life, you want half of it left. So you started with 4.8 grams. Half of that is 2.4. So that's the amount you have left. Well, that's a y value. So in my equation, I need to plug that in the y spot. So 2.4 equals 4.792.996 to the x. All right? And I have to solve this for x. Well, this is what we did in our last unit. I need to divide by 4.792 first. Gives you close to 0.5. And where is x? X is in the exponent, so you have to take the log. Log of 0.5. We'll go ahead and throw x in the front. Log of 0.996. Then I divide by log of 0.996. So log of 0.5 divided by log of 0.996. In your calculator, you get 172.94. So that's the half-life. All right, next example. The average daily amount of waste in pounds generated by each person in the United States is given below. This includes all waste, industrial, demolition, and sewage. The given data is best represented by a second-degree model, where X is the number of years since 1980. So we've got two important things right here. Let's first talk about a second-degree model. That means a quadratic, because it's X to the second. So we're going to be doing a quadratic equation. They're telling you that X is the number of years since 1980, so you have to follow that direction. So 1980, how many years has it been since 1980? 0. So that turns into a 0. Then 1985 would be 5 years. 1990 would be 10. 1991 would be 11, 12, 13, 14, 15, 16. Okay, so when you put that in your calculator, you have to use the new numbers. You need to put in 0, 5, 10, 11, 12, 13, 14, 15, and 16. 3.7, 3.8, 4.5, 4.4, 4.5, 4.5, 4.5, 4.4, 4.3. All right, it wanted a quadratic, so when you go over to calc, down to number 5, and we're going to go 3 decimal places. Okay, so you got to fill in the formula. So the equation is y equals negative 0.004. You put an x squared next to your a value. Plus this one rounds to 0.12, put an x, plus 3.593 is your c value. B says, predict the amount of waste produced per day in 2010. Well, 2010 is a year, so that's an x value. But you have to make sure you do the number of years since 1980. So let's subtract 1980, and you get 30. So x is 30, and we're going to plug that into our equation. So on the main screen of the calculator, you would do negative 0.004 30 squared plus 0.12 times 30 plus 3.593. And when you type that in, I'm doing it right now, do it in your calculator as well. You get 3.593 is your answer. All right, last 2 problems. In a physics experiment, a lead ball is dropped from a height of 5 meters. The students record the distance the ball has fallen every 1/10 of a second. Write a power equation that models this set of data, this data set. So you're going to put it in stat. And I've already done that. Feel free to pause the video if you would like to do it yourself into stat. That would be great. And for your power function, you've got y equals 4.962. You put an x, and the power is 2.003. All right, how long will it take the ball to be 3.5 meters high? Well, meters is here in the table, which is a y value. So y is 3.5. So when I plug that into the equation, I need to do 3.5 equals 4.962x to the 2.003 power. All right, I need to solve that for x. The first thing I do is divide by 4.962. And that gives me 0.705 equals x to the 2.003 power. All right, well, to get x by itself, you have to get rid of the 2.003. That's your power, so you would take the root, but you're going to put 2.003 on the outside. So hit the math button on your calculator. And go down to number 5 and hit over, and you're going to type in 2.003 on the outside, 0.705 on the inside, and you get 0.84 is what that's going to round to. So x is 0.84. Okay. And that's seconds. All right, how high will the ball be in 1 minute of falling? Well, 1 minute is time, so that's an x value, but you have to be careful. X is measured in seconds. So for 1 minute, that would be 60 seconds. So I need to plug x equals 60 into my equation. So 4.962, 60 to the 2.003 power. And you should get 18,083 meters. Which is impossible. It's dropped from a height of 5 meters, so it has hit the ground at this point. But that's if you're being technical about it. Okay? All right, the last one. The table below represents the amount of coal production in metric tons from a small mine in northern British Columbia. Which model best fits the data? So for this one, they don't tell you anything about X being the number of years since 1950, so you're going to put it in exactly like they give it to you. (1950, 1960, 1970, 1980, 1990, and 2000, 882, 889, 894, 894, sorry, 899, 905, 909. All right, which model best fits this data set? So we have to go to all 4 of these and write down the R value. So stat, calc, we'll go to linear first. The R value is 0.9976 for linear. Then I want to go to exponential, so stat, calc, exponential, and that one, the R value is 0.9974. All right, logarithmic, stat, calc, it's number 9. All right, that R value is 0.9978. And the power function, stat, calc, power function is A, which is 0.9976. All right, the best one is 0.9978. That's the biggest. It's closest to 1. How did you determine that this was the best model? Because it was closest to 1. All right, so predict the amount of coal production in 2005. So 2005 is a year, so it is your X value. But I don't have an equation to plug it into yet, so I need to go back and get the equation. We know we want a logarithmic equation. So in the calculator, I'm going to go back to stat, calc, and go back to log, and I need to write down that equation. All right, so that equation is y equals negative 7154.888 plus 1061.007 ln x. So I'm simply going to plug 2005 into the X spot and type all that in my calculator. Remember, the ln button is next to the 4, and you get 912.372.